Chapter 14 is about chemical kinetics. Chemical kinetics is a study of the rate with which reactants are converted to products. Another way of saying this is it's all about reaction rates, how fast reactions happen. Some happen fast, some happen slow. That's what this is about. There are four major things that are going to affect reaction rate: the physical state of your reactants, the concentration of the reactants, the temperature that the reaction is happening, and whether or not there is a catalyst. For physical states of reactants, and really for all of these, it's all about collisions. The more these things can collide with one another, the more reactions are happening, the faster they are happening. So the more molecules collide with each other, the more rapidly they're going to be reacting. So gases tend to react quicker than liquids. Liquids tend to react quicker than solids, and you can get solids to react pretty fast if they have a large surface area. What that means, guys, is you just grind it up. Grind it up to increase the surface area, make more of it coming into contact with whatever it is you're reacting it with, and you can make it react faster. The concentration of the reactants. If you increase the concentration, that means there's going to be more of it in there, so they're going to start colliding with each other more often. If you put more of it in there, crowd it a lot, this is going to cause large rates of reaction as well, so this is going to increase our rate of reaction. And if you heat it up, they're going to come into contact with each other more often. They also are going to have more energy when they come into contact with one another, making them more likely to interact with one another. So that is also going to increase the rate of reaction. Catalysts are substances that you can put into the reaction that aren't actually part of the reaction. They cause the reaction rate to increase, cause it to go up. However, they don't actually do anything as far as being a part of the reactants or the products. There's something, and we're going to learn how catalysts work in more detail in a little bit, but there's something that just causes a reaction to go faster. We did one of these in Chem 1 where we took hydrogen peroxide, we put some manganese dioxide in it. Hydrogen peroxide naturally decomposes when it comes into contact with light, but you put some manganese dioxide in it and it makes it decompose really, really fast. And when you get all done, you're left with some water, which is what the hydrogen peroxide decomposed into, water and oxygen, and all that manganese dioxide that you originally put in there. It doesn't get used up. Biological catalysts that are found in biological things like our bodies are called enzymes. So let's take a look at this question here. It says iron oxidizes in the air very slowly. So what are some of the ways in which we could increase this? Just look back over here. We could grind up the iron. We could take the iron and we could put it in really, really concentrated in oxygen gas. We could heat the iron up and the oxygen around it. We could put a catalyst in there with the iron, like salt water is actually a catalyst. This is the reason why whenever you are driving your car out when it's icy and they've put salt in the roads, this is the reason why you need to wash your car after you drive it, because the salt acts as a catalyst, and it causes the metal in your car to oxidize faster than it normally does, and it can make your car rust out. A reaction rate is how much the concentration of your reactants is changing over time. A rate is anything divided by time. If we look over here at this equation right here, this shows that the change, or delta means change, in the concentration of A, the little brackets stand for concentration, divided by your change in time is equal to the rate of your reaction. This is one way to describe reaction rate. Something that's interesting about reaction rates is they will actually go down with time. The reason why a reaction rate will decrease with time has to do back here with this concentration thing here. The higher the concentration of reactants, the faster it goes. So whenever things start reacting, your reactants start to go down. Their concentration goes down. You have two things react, they make a product, and suddenly there's less reactants. So as the concentration decreases, the rate decreases too. That doesn't mean that the reaction stops. It just means it starts going slower and slower and slower. Now, since rates are constantly changing, what that means is that we tend to express rates either as instantaneous or as initial rates. Instantaneous rates are the rate at a very particular point in time. An initial rate, which is the main one we're going to be talking about, is the rate at time 0. So the rate of the reaction right when you start the reaction, the instant you mix the reactants together. If you take a look at this graph here, this is an important graph that shows us the reaction of nitrogen dioxide. In this reaction, we have two NO2s decomposing into two NOs and into an O2. This graph over here is showing us the rate at which the NO2 decomposes and the rate in which the NO2 and the O2 is made. Notice that at time 0, the concentration of NO2 is 0.01. Concentration of NO and O2 are both 0. But as the reaction progresses, the concentration of NO2 starts to decrease. And the concentration of NO and O2 are both going to start to increase. Notice something that's kind of interesting here is that the rate of decrease for NO2 and the rate of increase for NO is the same, just one's going up and the other one's going down. But the rate for increase of O2 is half that. And the reason why is because of those numbers right there, 2 to 1. That mole ratio, for every 2 moles of NO2 that are lost, we gain 2 moles of NO, but we only make 1 mole of O2. And so our concentration is half of the O2 that it is for the NO. Notice also that these things level off right about at the same place, right around here-ish somewhere. The slopes of the rate start to reach 0. This point right here is going to be our point of equilibrium. This represents an equilibrium reaction, a type of reaction that's going to be really important to us in the future. So another way to describe this is going to be using this equation right here, where the rate of change of NO2 is equal to the rate of change of NO, which is equal to twice the rate of change of O2. And so this is just a different way to describe the same thing that's right up here.